The next presentation is by Robert Gagnon.
Okay, thank you very much. First, I'd like to thank the organizers for the invitation. It's a great opportunity and honor, really, to participate in this workshop. So I'm presenting on the physics of ice crushing. We've had a number of presentations that deal with ice crushing, and ice crushing occurs in many contexts. Most of what I'll be talking about is ice crushing in the brittle regime, and so we'll just move right on here. So this is the take-home from this presentation. I have a lot of material to present, probably won't get through it all, but these are the essentials. So this is the conceptual model, and when I'm using that word conceptual in sort of a loose way, because all of this so-called model is based on physical observations, visual observations, instrumental observations from experimentation over long periods of time, work that I've done and work that many other people have been involved with. So essentially, when ice is crushing against a flat surface, let's say this platen here, I'm not showing the whole bulk ice sample here. This is just the ice that's in the region of the contact with the surface. So the original ice is shown here in blue, and basically it's relatively intact during the crushing. There may be some cracks in there and so on, but the strength of that ice is still quite good. And as the ice is moving against the platen this way, there's crushing happening, and actually on the sides of the ice there is the crushed material, the crushed ice, and the crushed ice is essentially remnants from spallation. So if you look at the image on the right, as this ice is moving towards this platen, stress builds up in the ice, and I've just shown one spalling crack that formed here. Very shortly after, and I mean on the scale of microseconds or milliseconds, that spall fractures. It becomes pulverized ice. It shatters, and then it joins the rest of the crushed ice at the sides. Now, as this ice is moving towards the platen, you will notice that I put in a red line here. That is an indication of a thin layer of slurry. The slurry consists of about 80% solid ice particles and about 20% fluid. And it is the flow of that slurry that enables the hard zone ice, this intact ice, which I'm referring to here. I'll be referring to it as hard zone ice. It enables that hard zone ice to get out of the way. In other words, the slurry layer, due to its viscosity during the flow, it melts that ice and also erodes it. And I'll get into more detail on the erosion a bit later. But that slurry plays an extremely important role in ice crushing. And we'll talk quite a bit more about that. So that's the essentials of the process. And now I'd like to mention a few types of apparatus that have been used to study ice crushing. This is a laboratory apparatus where you have a platen, a crushing platen, that pushes against an ice sample that's held in a holder. And it turns out in this particular apparatus that the holder itself had a transparent bottom, or top in this case, so that one could use a mirror to view with high-speed video that looks down through the ice holder device and through the ice itself at the surface of the platen during crushing. And the platen was fairly heavily instrumented also with pressure sensors, a liquid sensor. So in the very center there is a pressure sensor, and in the center of the pressure sensor there is a liquid sensor. It was a resistance type device that could detect liquid that was present during the crushing. And also, I didn't mention there's a thermocouple there, so there were temperature measurements also made during the crushing. So this is a figure, you've already seen that, Kai showed it earlier. This was one of the indentors, the one that Kai made reference to. It was a flat indentor. It had a number of piston type, traditional diaphragm type pressure sensors on the front. It also had the piezoelectric type array of pressure sensors that the guys from Finland supplied for that study. And then we had the Lexan window that was in the center, and that's why you see video camera here. So we were able to look at the physics of what was happening, have visual information in situ. Another type of apparatus that we developed at NRC was an edge crushing type device where you have a piece of ice and it's constrained by glass plates, thick glass plates on the side, and the crushing is done from the top. This is the crushing platen that just slips down in between the two glass plates, and crushing occurs. You can look at it both from the side to see what's happening, but also, and very interestingly, some of the platens were transparent themselves, made out of acrylic, so that you could use another camera to look down through the platen, through here, down to see the action where the ice was being crushed. And in addition to that, we had a pressure sensing technology which we developed. Essentially it was acrylic strips that had a sort of a rounded surface on the top, and this is exaggerated here. The curvature was not that great. And then when a load was applied, the amount of contact, the width of the contact, was a direct measure of the pressure. So I actually have a little mock-up showing how that works for anybody who would like to see that afterwards. That technology we've used extensively, both at small scale and at big scale, to measure pressure during ice impact and indentation. So Kai already referred to some of this slide. This was the early work by Franson and Olofsson, showing hard zones that you could see here, and crushed ice around the sides for different shaped ice features. This was the vessel that Kai cut a hole in and put a window in, and these are the hard zones, his linear shaped hard zones that developed as a result of that.
That's the vertical thing.
That's a bracing thing, right, Kai, for the window? Otherwise, the
Correct. We supported that because we were afraid of the window breaking. So.
And then the boat sinks. Yes. Good plan. So, and this apparatus was, I find it interesting, these three papers came out in the same year. This paper was what I did with John Mulgard. We were actually studying crushing friction. We had a rotating wheel here, and we were crushing an ice sample against the rotating wheel. At one point, we had the idea, well, let's have a look at what's going on at the interface between the ice and the wheel. So we cut a hole in the bottom of the ice holder and put a thick glass plate in there so we could look through the glass and the ice. And what we saw was very similar to this, only not linear, because the shape of the ice was different. We saw the hard zone regions surrounded by crushed ice, and these are just the cracks, peripheral cracks on the sides. But actually, this paper was the first discussion of the slurry layer in the literature that I'm aware of. I don't think anybody else had anything to say about it prior to this paper. So, and I'll say quite a bit more about that as we go along. This was work by Claude Daly. Claude was focusing on spallation and was able to generate sawtooth load patterns just purely from the spallation. Claude wasn't dealing with any of the physics of what's happening in the hard zone region, or how in fact the indentor is enabled to move down through this hard zone region. Those descriptions were part of the work that we were doing at NRC. So that was a bit of historical apparatus and some experiments. So just to look at some data, and some of this will be familiar from previous slides. So this is from a small-scale lab test. And in this case, this is a load record, typical sawtooth load record. Every single load drop here is associated with a spalling event. And so this is the same drawing we had before. So here's your hard zone ice, here's your crushed ice, and here's a spall coming in. When that spall fracture causes the spall to break away, there's a drop in load, and that's what each one of these sawteeth is associated with. And interestingly, when that spall shatters, the load then transfers to the remaining hard ice. And that is the source of the spike in the pressure that Kai referred to before. And there's some really important things that happen during that spike. That spike happens on the scale of 950 microseconds. So it's a very, very narrow event, but some important things happen in there. Oh yes, and this is the actual displacement of the ice towards the platen, and due to the compliance of the ice and the platen that Kai referred to earlier, even though the nominal crushing rate is linear, is a fixed rate, the true crushing rate has this stepwise type pattern where on the ascending parts of the saw teeth, the indentation is slow, or the amount of ice getting out of the way is slow, and then during the sawtooth or the load drops, you get a ratcheting effect. So the relative movement of ice and platen is very fast, many times that of the nominal value. This is field data from Hobson's Choice, the ice island work, and same deal. You see the same things that are happening at small-scale lab tests and the medium-scale indentation tests for the ice island. So this is the sort of stepwise displacement record. This is pressure data from, there's two types of pressure sensors here, the diaphragm type traditional ones and then the piezoelectric ones that Kai referenced. And in each case you see these spikes that occur. The spikes are associated with that transfer of load. When a spall breaks away, the load transfers to the remaining ice and you get a spike in pressure very fast. And this is the load record for that. Actually, for the ice island, I had put a thermocouple in the center of one of the pressure sensors. And we got some really interesting data from that. So this is the temperature measurement from that thermocouple. And as you can see, the ice started out at around minus 8.5 or so. And by the end of the test, it was up to 0, indicating that there was some liquid present. So if you look at the expanded views of these three records, you see the stepwise motion. You see the steps associated. The line I put here shows the synchronization between the types of events. So when the when the indentation is fast during a load drop, you see it here. And corresponding to that, the temperature would have a bump up at the time when those spalling events happen. And the reason for that is that every time a spalling event happened, you would have a new jet of warm slurry that was squishing out of the hard zones, and the wet material that was left over from previous events would also start moving again. So you'd have some fresh, warm material that would sort of move over the surface of the temperature sensor. So you'd see a bump in the temperature when that happened. But there was also the general rise. Everything was just heating up during the whole event. So that's why you see this rise here. And eventually it got up to 0 degrees. The liquid sensor that I mentioned that we used in some of the small-scale laboratory tests gave some really interesting results. And this is going back several years. So the concept of liquid being present, the slurry being present, dates back to around these days and somewhat earlier. So it's not a new idea. So what we see here is, here I've called it liquid thickness, but really it's the amount of liquid that the sensor detected. So on average, during the ascending parts of the sawtooth load pattern, it was sensing around a certain amount of liquid. And then during the load drops, which caused the pressure spikes, there was much more liquid present, and that's what these spikes here correspond to. And what that means is that the slurry layer, the thickness of it varies. So on the ascending part of a sawtooth load pattern, the slurry layer is around 0.02, 0.03 millimeters in thickness, and during the load drops, it shoots up to about 0.17 millimeters in thickness. So, got to show some video because a lot of this work is based on visual observations. So the first thing we'll look at is Hobson's. So this was a big indentor apparatus. You saw the schematic for it earlier. The indentor that's on the front of this one happens to be wedge-shaped. Now, I decided to stop it here for a reason. One thing, of course, is, that this is the kind of experiment that you need to do to understand what's going on at these scales. These are not cheap experiments, as you can probably imagine. But the reason why I stopped the video here is that all along this face we were doing crushing tests against different shape features. And so here was an earlier test, and the hard zones that I've been referring to, you can see one right here. And you see the crushed ice on the sides. Same kind of features that you see at all scales that I've done experiments with. So to see what happens on the inside of the indentor, so that's running at almost real time. So we're looking through a window. I'm going to have to walk you through this. We're looking through the window. It turned out that the ice was quite bright. We didn't need to have any lights. And this was a truncated pyramid feature that we were crushing against. So you see the window here with bracing on it for the same reasons that Kai had bracing on that vessel. But the first contact with the ice, you see it here. So some crushing material appears dark because of sunlight. The ice itself was bright. So the white is pristine ice, and dark material is ice that's been crushed. So if we just so now we're starting to see some features. What's happened here, unfortunately the bracing covers some of the view, but you could see enough. You see that X shape starting to develop, and that's because spalls are happening on the edges of this pyramid. So one spall here, another here, another here, another here. And the X is the pristine ice where the pressure is high, 20, 30, 40 MPa. And the spalled ice, which is beaten up and pulverized, the pressure is around between 0 and 10 MPa. So as this proceeds along, you can see new spalls popping in. So on the left here, you see that spall? So a big spall has just come in on the left. And as this proceeds, the material that was created by the spall moves away from the hard zone area. So spalls form, material's crushed, and then it just is squished out of the action area. So this just keeps happening. Another big spall has just come in at the right in this case. So it's not there now. There it is. You see it. And this just repeats around the four corners. You see one just came in there at the bottom, side, another side, bottom again, side, and so on. So we're seeing the same phenomenon at this large scale that we were seeing at for small scale tests. And then the next video, I just need to go back to right. So this is a laboratory test of the sandwich type, where we were doing edge crushing, where we had the glass plates confining a flat piece of ice, and we were crushing using a platen that just fitted in between the two glass plates. So the platen here is steel platen coming up. Now what you will see here is some in-plane fractures in the ice. You will see some spalls happening at the sides here, but most of the spallation is actually happening on the back side that you can't see. I have another video to show you what that means, but the purpose of showing you this slide, whoops, hope I haven't lost that. Oh, that's too bad. Just a moment. Sorry, for some reason that video shut down. So I wanted to point out a few important things here. So one thing is that the ice is staying intact. It's got some cracks in it, but the hard zone is actually here. And the slurry layer, you can actually see it here, and in fact we were able to get a thickness measurement from that. And you can see the slurry flowing out towards the viewer, and flowing down the front face of the platen. That experiment was done at -10, I think, -12. The slurry flows out of here, but it also flows out to the sides and wets material there. Just to explain a bit what I meant when I said that spalling was happening on the back side. This is the top view through the crushing platen, and I'll run it at real time and then walk you through it. So we're looking down through the platen at the so that hard zone ice that I was just referring to, we're looking down through it now, whereas before we were looking sideways. So this is intact ice. Spallation is happening from the back side, and where that ice is in contact with the platen, you have the slurry being produced and quickly being ejected. And then now, so this is some more high-speed video. This is very high-speed video. This is 30,000 images per second. And this is small-scale lab test. We have a sort of a pyramid-shaped piece of ice that's crushing against an acrylic platen, and we're looking through the platen at the ice. So just run it in real time. Actually, that's not real time. If you run it in real time, it looks something like this. It's over that quickly. So very hard to see what's going on. But we have the luxury, with the advent of high-speed video, to be able to see quite precisely what's happening. So this is a hard zone region, and this is crushed material. And what you will see when we run this is spallation events. So every time one occurs, the big one occurred there, but you still have the remaining ice intact. And every time a spallation event happens, you have this drop in the load. And one really interesting thing that we were able to determine from this type of video was we got a measurement of the slurry layer thickness due to a few instances where we were able to see ejecta coming out from a spalling event. So down here, when I run this, you're going to see some material coming out from the hard zone, and a thin plate of the slurry ends up coming out through the side, and it happens to fly over towards here, and it's rotating. And by the time it gets to the edge, it's on edge, and we were able to get a thickness measurement of that plate. So just let that run. There it goes. You see it right here. Run that back. So just going slow. The event is about to start. There we go. So this is material forming It's the slurry coming out there and forming a plate, that shiny object, which we're able to get a thickness measurement from later.
Sorry, how do you know the plate is the thickness of the slurry?
Because that's where it came from. You could see it coming out the edge.
Like you know that it's full thickness?
Well, that's a good point. The thickness that we measured was consistent with other methods which I'll refer to, was consistent with the other methods that we used to get a thickness measurement. So, but the whole slurry is in motion when it's being squished out, and it just appeared that what was coming out of there was in the form of a plate. It had to be a wet plate because it was 20% liquid and 80% solid. So just recapping on some of those experiments, this was the lab test where we had a pressure sensor with a thermocouple and a liquid sensor on it. This is hard zone ice here. You can see through the hard zone ice because it's not damaged, and here's fractured, shattered spall debris around there. This was from the ice island experiments, that X shape that formed, the spallation that occurred there. And this is just an example of a before and after shot for a spall that occurred during these tests. So you see a contact zone here, hard zone region, and shattered or crushed ice around that. And then a spall occurs in this region, so a portion of that contact area shatters. There was a question earlier about thin sections. These are some thin sections from growler impact tests. Growlers are small, quite small icebergs, about the size of a car or less. And so we did some tests in our laboratory where we were impacting growlers with a device in our ice tank. And these are thin sections from the impacted area, so that's an impacted surface there. Another one here. So this is the original iceberg ice. There's no change in the iceberg ice structure associated with these impacts. Those are the original grains with the air bubbles and so on in there. And you can see some remnants of this slurry layer that I was talking about. You see that up here. Very, very fine grain material at the top. I also mentioned that the hard zone region is not necessarily pristine in terms of not having any cracks in it. These are images from one of those sandwich type tests where you can see cracks that are developing in the ice, but they don't influence the strength of the ice that much. And in fact, you still have the hard zone region at the top, and you have crushed material on the sides that develops. This is the output from a pressure sensor. It's inset at the same scale to these images, so that the pressure is indicated by the width of the contact here on the pressure sensor. So that corresponds to this hard zone region up here, and same sort of thing down here. High pressure here, lower pressures on the sides. We've already seen this. I think I mentioned that we were able to get a liquid or the slurry layer thickness measurement from here that matches pretty well with the other one that I mentioned. Actually, that's some of the slurry layer left on the platen after the test, and so that's kind of frozen onto the platen. We also did bigger tests, same idea. In that case, we had a bigger indentor, bigger ice, 3 pressure sensing strips instead of 1. And same sort of thing, the ice has some fractures in it, but the hard zone is here, and the crushed material is at the side, so the pressure reading shows that the hard zone is there. This pressure sensing technology is really interesting because it's transparent, so you can actually see through it as you're getting a pressure measurement, so you can see what's happening. You can actually see the dark aspect of the hard zone through the pressure sensor. Same thing here. Now, this is a bit of history. There were some experiments done by Jordan and Timko back in the 80s, and they were pushing an indentor onto the edge of an ice sheet in one of the ice tanks at NRC, and of course there was fractures in the ice that really don't affect the strength too much, but they observed crushing on the business end of things, and they made an assumption from their observations that because they saw this crushed material here, they assumed that that crushed material was through the full thickness of the ice. So they came up with this notion that there was a thick layer of pulverized material between the ice and the indentor, and that somehow that could create spall or create sawtooth load pattern and so on. And this idea has persisted to today. There are some people that still view things this way. However, if in those tests, if they had been able to look edge on to the ice, like in these tests that were conducted by Maton and his colleagues, they would have seen that the ice takes on a shape when it's in contact, like the mountain peaks as Kai referred to them, but the actual contact is more central. It's not a uniform, mashed up conglomeration of ice in front of that indentor. And same thing for the Joya tests that were conducted in Japan, edge-on type tests, and you get a hard zone that develops through the mid thickness of the ice, and crushed ice is above and below that. This is this is showing the same apparatus as before for the tests that were conducted in the lab, and this is just a recap for this is polycrystalline ice crushing against the platen, and this is the left image is before a spall and afterwards. So you see spalling event here. You see a piece of that ice structure has shattered to become crushed ice. Same thing here. You can actually see some of the crystal features in the ice before the spalling event here, and again, the hard zone has reduced in size as a result of the spalling event. Now, don't worry, you don't need to read all this. Basically, it's referencing a number of experiments that were used to get some information about this slurry layer. The slurry layer is so important. So we had the liquid sensing experiments here. We also had the case where we could measure some ejecta from the hard zone and get some edge-on measurements of thickness from that. We also had a measurement from the thick section crushing, where we could view the thickness of the layer, get a measurement there, and those values were consistent. In addition to that, you can make some simple calculations just determining the amount of hard zone material that's removed during a spalling event just from your compliances and instrument measurements, and you know the amount of energy that went into that from your system, and you can determine how much melt was produced. So from all those pieces of information, you can determine that the slurry layer for the lab tests at least is between 0.02 and 0.17 millimeters, and that the liquid fraction is about 16%. And then the question is, how does that slurry layer form if it's 80% solid material? I'm about to finish a paper that'll be submitted fairly soon that explains that. Turns out that when you pressurize ice very rapidly, which is what happens during these events, you put the ice into a superheated condition. And when ice is in a superheated condition, and I'm not referring to pressure melting, I'm referring to adiabatic formation of melt figures in the ice. And melt figures are these little features here. The scale on that box, that's like 2 millimeters across. So this was from ice experiments where we were hydrostatically compressing small samples of ice and observing melt figures that occurred that nucleated at the surface and propagated into the ice. A melt figure is a negative crystal, if you like. It's basically a liquid-filled, sort of faceted type structure. Looks like fern. But these will grow as a function of the amount of superheating that one applies. So to explain how pieces of ice can break away from the hard zone surface, Tyndall figures, or these melt figures, they were named after John Tyndall, form, and they go to a very shallow depth, like fraction of a millimeter within the hard zone surface, and kind of that matrix of tenuous melt figures in there, they're very thin, like 20 microns in thickness, and they can soften the top surface, like a sub-millimeter thick top surface. And then the slurry that's present and flowing will just basically rip it off. And so it's kind of like a self-generating production of a slurry that's 80% solid or particles and 20% liquid. So just since this is about math, I don't have much math in this presentation, but I do have a challenge. This is the original drawing that I presented earlier, and I want to focus on the slurry layer and say that the creation and flow of this slurry layer involves several aspects. One is that it's two-phase flow. The second is that there's erosion of particles from the hard zone interface, and that becomes entrained in the ambient flow of slurry. And then there's the surface weakening shallow depth melt figures that form during the pressure spikes. Yeah, I didn't mention that. It's during the pressure spikes that these melt figures occur. And then there is also melting of the hard zone surface due to the viscous flow of the slurry layer. It has a viscosity, it's high pressure, so there's energy, heat created just from the flow that does some melting. There are also very highly localized and rapid temperature variations in this situation and extreme temperature gradients. So in my opinion, the pervasive and important slurry layer is the most mathematically challenging of all phenomena in ice mechanics to describe, whether analytically or using numerical techniques. Ice on ice. If you crush ice against ice, what happens? It turns out that this is an experiment where we have a flat ice feature in this confining ring, and we have a sort of pyramid-shaped piece of ice that's going to crush against that. And it turns out that, lo and behold, the same phenomenon happened as would happen if you crushed ice against some other material, flat surface like acrylic or steel. So again, these are before and after spalling events. This is a hard zone, and a piece of the hard zone has shattered. And this is the crushed ice around the sides. This was another event in the test. This was a large hard zone, and a big piece of that shattered. So you see this same kind of physics happening when ice is crushing against ice, and this is really important, for ice crushing within glaciers, but also for ice flows that are rubbing against each other, sliding, banging into one another. Same kind of physics is happening. These are just more images, examples of hard zones and crushed ice for ice on platen type crushing. This is polycrystalline ice, two examples. Polycrystalline ice tends to give you more dendritic type hard zones, and this is ice on ice. This is polycrystalline ice, and it's dendritic, as I mentioned. But when you have ice on ice where you have single crystals, the hard zones are much more blobular in size and or in shape and extent. I'm running short on time. I did want to get to something that's very important, and then we'll just come back to here. Just a moment. I did mention crushing friction, and I wanted to get to that. So, when you have ice crushing against material, then you can have instances where the ice is sliding laterally besides crushing. And it turns out that for a whole other topic, we had to perform some experiments using a very rough surface. And Erlen has an example of it he can pass around to show what I'm referring to. We had to do some experiments where we were crushing ice against rough surfaces. And so rough on the scale that you see here, which means prominences on the surface that are sticking up by a millimeter or so. And so we were crushing ice against that surface, but also sliding the ice at the same time. And so we had friction data that looked like this. One thing to note is that all of the data are very low, yield very low friction coefficients given the roughness of that surface. You'd probably expect friction coefficients on the scale of 0.5 or higher, but these are very low values. So for the three, we had 3 cases of the downward crushing, and this is the sliding rate. So each line corresponds to one of the downward crushing rates. And in any case, you can see here that these values are really low. In fact, we had some data there for flat steel plate, and many of these data points are actually lower friction coefficient than for flat steel plate. And if you get your hand on that thing that's being passed around, you'll be surprised to hear that. So the reason for that is some very interesting friction phenomenon, which I don't think has been described before. So what happens is the key component here is that slurry layer. And if we look at the profile of the surface that we're crushing against, as the ice is crushing down here, the slurry layer is created at all the surfaces where the ice is making direct contact. But because the ice has a sliding component, it is creating a gap on the leeward side of those prominences. And that gap, this is an expanded view of one of the prominences. So you see the slurry being created up here, and it's also created on the front side that you can't see. But on the back side, on the leeward side, there's a gap that forms because we're melting ice here. So a gap forms, and that gap fills in with the slurry that's flowing from the horizontal flat surfaces. And so it creates a back pressure. It's a pressurized slurry. And by definition, the friction on this rough surface is determined by the difference in force on the front side and the back side of that prominence. So when it fills in with slurry that's pressurized, you have a balancing act. And you end up, as long as you're doing some crushing, you end up with very low friction coefficients, even though it's a very rough surface. So that has a lot of implications, I think, for many different reasons, for many applications. So I'm just going to go back to where I was. And then we'll have a couple of minutes for yeah, I won't get through all this, but I do want to show you one. We built a big device that was a square meter in size that could measure the pressure using the technology that we have. And we put that device inside a double pendulum impact apparatus, and we had ice over here. So I'll just show you the video. So here's the ice, here's our impact module. You see the pressure sensing surface here, completely covered with pressure strips that we developed. So without having that pressure sensing technology, you'd never know what happened during that event. It was so short. But we can see quite well what goes on. So things happen quickly, and I'll just walk you through that. By the way, this gap here, there was a secondary pressure sensor on the surface, so we didn't have the other technology there. That's why you see this hole. But what's happening is that when it first makes contact, the pressure is uniform, and then, if I can just get it to click, spallations are happening right at the start. Whenever that happens, the pressure is transferred to the remaining hard zone ice. Just click along here. So spalls are happening at various times, and the remaining ice is the hard zone ice. And that carries on. The light blue stuff here is the actual crushed ice that's flowing away from the hard zone. So as you can see, the shape of the ice hard zone can be, and this goes back to what Kai was saying, when you have a round shape, then the geometry, there's somewhat of a random aspect to how it can evolve, as opposed to having 5 minutes. So I'm just going to call that the end, and take some questions. Yeah.
Any questions or comments?
Oh, I think these images are fascinating. And by looking at what you're seeing really helps to know what's going on. But I got to ask one question. You've used the term hard zone many times here.
Yeah.
What is it? What do you imagine it to be?
The hard zone is relatively intact ice. may have a few cracks in there, but in some experiments there's hardly any cracking in it at all. So it's the original ice, and soft zones are the crushed material that are shattered spall debris at the sides of the hard zones.
By saying it's original ice, are we meant to understand that
The crystal structure hasn't changed.
it has not changed one little bit?
Not in thin sections that are cross-polaroid filtered thin sections and stuff that I've...
Is it significant at all that both in the line contacts that Kai spoke of, and you now too, and then these hard zones, do you think it's significant that these zones occur within the region where the confinement on the ice is highest? That is, the degree of triaxiality is pretty high.
Well, the shape of the ice is what determines where the hard zone is going to be. And in addition to that, the crushed material that's coming out of there has, it supports load also, but it also provides confinement on the hard zone. But generally speaking, the geometry of the original ice feature determines where the hard zone is going to appear and its shape.
And that also determines then the stress state within the ice.
Yes.
You know what the ratio of the principal stresses is? Say the ratio of the highest to the lowest principal, or the lowest to the highest principal stress is in the hard zone. Can you tell us that number?
Not offhand. I mean, I can
Yes.
tell you that the pressure, the interface pressure is, between 20 and 70 MPa.
When you say pressure, you mean stress, not just P1 plus
Well, yeah, the pressure inside. I'm talking the interface pressure. What? If you had a pressure sensor at the interface, that's the pressure I'm referring to. You're referring to the internal stress in the ice and
in
so
the
on.
ice. That's
Yeah, which is going to be less than that.
You don't know that number.
Well, you can, the simple mathematical expression will give you that, right?
You only got a few minutes here, John.
So, just as a comment, and then I'll ask a question. You consistently refer to spalls, and I guess I'm thinking that part of the time you mean separate crack growth events, which may be leading to the eventual nucleation of a complete spall.
Yep.
And the other idea with your mathematical challenge, I'm wondering whether there's quite a complete analogy between slow indentation in very high temperature ice, which it is, and the decades-old work on high-speed penetration mechanics, where they assume at the outset that you have an inner solid body, you have an outer fluid layer, and then you go back to a solid. So a lot of your mathematical challenge could be well established, and I think quite old.
But it occurs in a
I'm
very
not actually speculating.
it occurs in a very thin layer, though.
I understand.
It's not in the
I
bulk.
think a lot of the mechanics is already done.
Okay.
Okay.
Yeah, it's very close what you explained to that so-called hydrodynamic model of impact on ice. But that one is rather simplified compared with results of your experiment, because it's assumed that main part of the ice is elastic,
Yeah.
linearly elastic. Then there is a line which divides crush ice and elastic ice,
Yeah.
and on that line, they remember the stress is yield stress,
Yeah.
right? So there is a free surface problem,
And it's a very thick.
it's
It's a very thick layer that
Yeah, very
those
thin
guys
layer.
are talking about.
Yeah, but your results are kind of different.
Yes.
Actually, this part, which could be elastic, it's very far. There is the crushed ice, not crushed ice, cracked ice, and then crushed ice. Right. So but if to take that hydrodynamic model as a basic model, I mean the base model, and then develop it further to include that cracking, then it could be answer your mathematical challenge.
Well, the Tyndall figures that I'm referring to, the melt figures, are cracks. They're liquid-filled cracks. They weaken the surface of the ice, and that's how ice is eroded away from the hard zone.
All right.
Okay.
Thank you very much.